All right, so new topic. All right, just new topic. New chapter, we're turning a page. All right, so now we're going to be looking at rigid bodies. So everything else, we were assuming they were particles. We were assuming that all the forces go through the middle of the object. But for rigid bodies, now these objects have size. And, you know, if you've got an object and you put a force on the edge of the object as opposed to the middle of the object, right? You would create moments which create rotation. So now we need to talk about rotation. Now we must be concerned with rotation. So obviously translation is what you think, but now let's talk about one thing though with translation. I need a pen. My red pen kicked the bucket while I was grading. All right, so let's say we've got a line on our page, right? Translation is motion in which every line remains parallel to its original position. So, you know, left, right, up, down. What about this? This right here is translation. Okay, this right here is translation. If the line remains in its orientation, that's translation. So you could actually have translation in a circular path. All right, we may do one problem like that. But then rotation is motion about an axis. Now, the axis could be, you know, in the middle, right? Could be on the edge, but also could be kind of off, you know, your center of rotation could be off of your object, all right? But rotation is angular motion, and general plane motion is a combination of translation and rotation, okay? So let's talk about rotation. Let's talk about rotation. So we can define rotation by angular motion. We can define rotation. So now instead of something like, hey, how many feet per second is that traveling? How many meters per second? We might want to know, hey, what angle per second is it rotating, right? We might want to know its angle per second. It's angular velocity, it's angular acceleration. Okay. Before we get to that, let's say we've got two lines on a sheet of paper. All right, pink, white line, a blue line number 2. Line number 1, we can define it as its orientation is θ1 from horizontal. You know, maybe it's 25 degrees from horizontal, and θ2. You know, maybe 50 degrees from horizontal. So we can define their orientation, θ1 and θ2, and the difference between those might be beta. Let me kind of draw beta right here. And so, would you agree that θ2 is equal to θ1 plus beta? Right, θ2 is θ1 plus beta. So maybe θ1 is 25, θ2 is 55 or something, and that angle difference would be like 30 degrees. What if you rotated your sheet maybe 10 degrees? That θ1 would become 35 now. You know, if you rotated it 10 degrees, then θ1 would change. So the change in θ2 would equal the change in theta 1, and beta would not change. I could put plus delta beta, but delta beta would not change. Do you see what we're saying? We're saying that every line on a rigid body changes by the same angle, right? The orientation of every line on a rigid body changes by the same angle. So if I rotate this paper 20 degrees, I don't have to specify, are you talking about this corner? Are you talking about this corner? Are you talking about here, here? The whole thing rotated 25 degrees or something, right? All right, but you only have one change in angle for one rigid body. Does that make sense? It's not like this portion of the rigid body changed 20 degrees, but this portion changed 40 degrees. No, the whole thing can only change one angle. Every line changes that angle. And so if we take that, let's say theta 2, theta 1, let's say the change per time, it's got to be the same. It's got to be the same theta dot. It's got to be the same second derivative, the rate of the change of the orientation. All right, so all lines on the same rigid body will have the same change in theta, and we're going to call that angular displacement. They have the same angular displacement. It's not like one side has different from the other side. If you calculate it once, you've calculated it for that whole rigid body. They have the same time rate of change of orientation, theta dot. So if I took the derivative of its orientation, then how much does its orientation change per unit time? This would be its angular velocity. This would be its angular velocity. We're going to call that omega, the Greek, right? Omega. It's angular velocity. And y'all are smart. What do you think theta double dot is? Angular acceleration. And we're going to call that alpha. Okay, so now let me clarify, because I'm not saying that this is equal to this is equal to this. There are three different values. But the rigid body has one angular displacement. All right, and let me not say 25 degrees. Let me say radians. Let's use radians as our angular displacement. Let's use radians per second as our angular velocity, and radians per second squared as our angular acceleration. All right, there are a lot of similarities with angular velocity and angular acceleration compared to our linear velocity and linear acceleration. So that's a good thing. We don't have to redo everything we've learned. Now we just have to think about it in angular form or angular terms. So instead of position, let's have angular position. I like kind of think of that as its orientation, angular position. So it's velocity. Now we've got angular velocity. And instead of linear acceleration, we've got angular acceleration. So if we start with some angular position theta, the angular velocity is still the derivative of angular position. And the alpha is the derivative of angular velocity. And even this right here, this VdV equals AdS, now omega d omega equals alpha d theta. Isn't that cool? Right? All those integrals, I could rewrite all those integrals, and all those integrals are similar as well. Anytime you had a V, now we've got an omega. Anytime we had an A, now we've got an alpha. Anytime we had a T, we still have a T, right? Time is not angular. Anytime we've got an S, now we've got a theta. How about those constant acceleration equations? Well, it turns out we have constant angular acceleration equations now. And I bet you could write them. Omega final equals omega initial plus alpha t. Omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial, or change in theta. And theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. 1/2 alpha t squared. And so we're going to still be doing derivatives. We'll still be doing integrals. And if you're lucky, maybe it's a constant angular acceleration. And you can use constant angular acceleration equations. The units we talked about, for the angle, it's going to be radians. For omega, radians per second. For alpha, radians per second squared. And radians are kind of a dimensionless unit. So when we're trying to make sure the units on the left equal units on the right, or make sure the units are homogeneous, radians are dimensionless. Okay, so the angular displacement, one rigid body only has one angular displacement. A rigid body only has one angular velocity. If it has an angular velocity of 5 radians per second, every point, that 5 radians per second is for the whole rigid body. If it has an angular acceleration of 2 radians per second squared, then that is the angular acceleration for every point. Okay, and you can imagine for a spinning, like a carousel, merry-go-round or something, that merry-go-round only has one angular velocity. But if you're on different points of that spinning, then you might have different velocities, right? Doesn't it feel like you're going faster the further you get out from the center of a spinning, merry-go-round or something, right? The further you go away, the larger your velocity, the larger your acceleration. How about the distance that you travel? If we were on a very large spinning platform, right? If we were on a very large spinning platform, think about the distance you would travel. If I'm out on the outside edge and you're close to the center, and we make one revolution, we both make one revolution, all right? But the distance I would travel would be that large circumference. The distance that person would travel would be a little bit smaller. The further you go out, the larger the distance s, the arc length distance s that you would travel, the larger the actual velocity you would be going. The wind would be flowing right faster on, you'd be going faster the further you get away, and also the more acceleration. So I think this makes sense. We already know this one, that S equals R theta. S equals R theta. So the distance that you travel would be equal to R times the angle that you rotate. And so we're going to say R is not necessarily the radius per se, but it's like the radius. It is the distance away from the center of rotation. R is the distance from the center of rotation. to the point you are interested in, right? Distance from the center of rotation to whatever point you're about to calculate the S, the distance that point has traveled. The velocity is, you guessed it, R omega, right? R omega is the actual velocity, the speed that you're going is R omega. So the further you are away from the center of rotation, the faster you're actually going, right? What if you were at the R is equal to 0, at the middle, you would be spinning, but you wouldn't actually be going any velocity. And A is our alpha, but we're just talking about A tangential. We're just talking about your tangential acceleration. And I don't need to put this, but this velocity is in the tangential direction, right? Obviously, there's no like normal velocity, but your velocity and your, whoops. So maybe I'm going to erase this. I'm going to kind of make a note that these two are in the tangential direction. What direction is the tangential direction? Well, we'll talk about it at this disk down here. Okay, but then also A normal. We know A normal is V squared over R, okay? And so same thing, our A normal is going to be V squared over the distance away from the center, which is like a rho. And we just said that V is R omega squared over R. Do you see what this boils down to? We have a new equation. That maybe this will be helpful. You could still do V squared over R. You could still do V squared over R. But if they give you the angular velocity omega on a silver platter, why not just do R omega squared to find your normal acceleration? And this is into the curve. This is into the curve. All right, so let's look at a wheel or a disc that is pinned at its center. This disc is fixed at its center, O. So it's just spinning about O. Pure rotation, spinning about O. So if we're interested in the velocity of A, and we know its angular velocity omega, the velocity of point A is R omega, right? This is R, the distance that A is away from the center, that distance R. What would its direction be? We kind of said in the tangential direction. The direction of that velocity would be in the tangential direction. So this might be kind of at an angle. We might have to figure out the direction of that VA. I think we've done this a little bit this semester. All right, that blue line, I'm going to call that a radial line. It's like a spoke of the tire. All right, that radial blue line, that's not the direction of the velocity. The velocity would be perpendicular to that spoke on a tire. The velocity would be perpendicular to that radial line. So I'm going to call that blue line a radial line. And so if this radial line, this is very small, maybe that radial line was 10 degrees from horizontal. If my radial line is 10 degrees from horizontal, then my velocity would be 10 degrees from vertical. They'd be perpendicular to each other. You could draw some triangles. You could do 10, 80, 10, then 80, 10, then 80, 10, then 80. Or do like me. If my radial line is 10 degrees from horizontal, then something perpendicular to it is going to be 10 degrees from vertical. Okay, my A tangential would be r alpha. So it would be along the same direction as velocity, assuming alpha is also in that counterclockwise direction. So A tangential and velocity are going to be along the same line. Now, one might be positive, one might be negative. They're going to be along the same line. A normal, where is A normal? A normal would be r omega squared into the curve. R omega squared into the curve. Okay. You know, maybe if you're lucky, maybe it just asks about this point. If you want this point, it's perfectly, you know, the velocity would be perfectly in the I. The normal would be perfectly in the J. But if you're asking some angle, you need to be able to give me the velocity and the direction for those. Okay, so I think we're okay, but we can preview the next few, but notice that it's similar. Some of them we're going to be taking derivatives. Some of them are taking integrals. Some of them we're going to have constant angular acceleration equations that we can use. Okay,